So I present an adaptive method for the numerical solution of a 2D Monge-Ampère equation. This is joint work with Gourzoulidis and Marco Picasso from EPFL and funded by the Swiss National Science Foundation. The 2D Monge-Ampère equation is an example of a fully nonlinear equation. Considering here a domain omega in R2, we're looking for a function u such that the determinant of its Hessian is given by data f with boundary conditions. In order to tackle the solution of this problem, we are going to introduce a flow problem, namely the time evolutive problem with the introduction of the time derivative, and we are going to look for the stationary solution of this problem. By noticing that actually the determinant of the Hessian can be rewritten as a nonlinear diffusion, we can actually see that this problem has the flavor of a nonlinear heat equation, where the nonlinearity in green is a cofactor matrix of the Hessian, and we have to make sure that this remains coercive, and that means that the solution we are looking for convex solutions. So in order to tackle this approximation, since the problem is nonlinear and rather stiff, we are going to advocate a midpoint rule for the time-stepping algorithm, which means that at each time step we are going to solve a Newton method, safeguarded, to progress to the next time step. And eventually our goal is to capture the stationary solution. From the space discretization point of view, we are going to introduce adaptive mesh refinement. We are going to work with continuous piecewise linear finite element, and this mesh refinement will be incorporated at some of the time steps. So very classically, we are going to look for the error indicator eta such that the efficiency index is bounded from above and below by a given tolerance. When you look at the weak formulation and its Galerkin approximation, you see that we are going to have to approximate the second derivative of the solution, the approximation UH, and that means that we are going to use mixed finite elements with regularization because we are working with piecewise linear finite element. So technically, we are going to use a residual approach. So the residual here in red will be on one hand bounded from above, very classically by the estimator in blue times the gradient of the error. On the other hand, we are going to bound this same residual in red from below thanks to the smallest eigenvalue of the cofactor matrix. And here we can see that we have an extra term in green that comes from the approximation of the second derivatives, and that will be more difficult to approximate. So when we wrap up everything together, we see that the gradient of the error will be bounded by two terms. The one in blue, that is a classical one, that comes from the residual, and the residual has one part of the residual on each triangle, plus one part composed by the jumps on the internal edges. And the second term in green is this gamma. This comes from the approximation of the second derivative that is theoretically more complicated to estimate. Nevertheless, when you look at some numerical examples, starting with a smooth one, so here where the solution is very smooth, we work on the unit square and we have an exponential function, we can see that all the indicators behave appropriately. Namely, in blue, red, or green, we all have first order convergence for all these indicators here, and error on the second derivatives. Now, when we turn to a non-smooth problem, so here we have a solution that has singularities in its gradient in the corner of the unit square. So here you can see that we don't have an optimal behavior anymore, because we have a singularity. And actually, we don't have the right convergence order for the H1 norm, but we do have the right convergence order for the L2 norm, as expected. And practically, we can see that the algorithm refines appropriately in the corners of the region. This is where the singularity lies. Finally, an example without an exact classical solution, still on the unit square, and here same conclusion. We see that we don't have an optimal convergence order for the error estimate. Nevertheless, practically, the algorithm refines very appropriately next to the boundary of the square domain because this is where the problem lies in the solution.